tutorial session. I believe we have this room booked for quite a while, until 4, so I don't plan on using all of this time. What I'm going to be going through is fairly basic. I'm going to go through it slowly, and we have time, so if you have questions, please interrupt me, ask, and then I might answer your question or tell you to ask again after. Just a quick overview about what I'm going to be covering in the tutorial now. So now that you've been working here for a while, we want to continue your education just so that you can continue to learn more about how virtual machines work and what the work around here that we're doing, and try to deepen your understanding of things that we work on the team. So I'm going to be going over what the tutorial will be. This will be a multi-part tutorial, and this is just the first session in many, hopefully. I'm going to be introducing the virtual machine we will be using in the tutorial to teach you how the different components work and see how they fit together. Then I'm also going to do a somewhat brief but thorough overview of virtual machines in general, and I'm going to see how a lot of the concepts from virtual machines are actually very generalizable, and they will come up in virtual machines for almost any language. Towards the end, I'm going to talk about just a little bit of setup you'll have to do before the tutorial. It's not as bad as for the other things you've had to do. This is just making sure you have the right pieces you need in order to build the code. And right at the end, I'm going to talk about just some tips for reading source code. Jumping right in, this tutorial is really just about furthering and deepening your understanding of virtual machines. So if you've been working already on OpenG9 or OMR for a while, you're probably starting now to get a sense of how the different pieces work in like very small amounts, and you might understand one component specifically, and you might understand another component somewhat well, and you have some idea of how the two work together, but maybe you don't yet understand how a complete VM works and how you go from just source code to something that can actually execute code. So this tutorial is intended to cover all of the basics so that you will start from something that is a very basic language all the way through to how you actually execute that code. The goals for the tutorial are, first of all, as I said, to learn the internals of how virtual machines work. And the second goal is to learn and get practice reading and writing code. We'll look further into what that means specifically later on. For now, we'll just focus on just really learning what it is that virtual machines are doing in the background so that you get a better understanding of the things we work on here. So this tutorial, as I said, this is the first session of many. We will be using a very simple, almost toy language, VM, where the idea is we want to make things as simple as possible so that you can understand all of the pieces from start to finish, and there's no kind of black magic that's going on that just makes things work without really understanding why it works this way. So there will be alternating sessions where we're going to start with theory, which is what this session is about. It's just the theory of how virtual machines work and how specific components of the virtual machine work, followed then by some application where we will be writing code to put into practice the things we've learned in the theory. So the schedule very roughly is, first of all, this tutorial where I'm going to introduce virtual machines and the TVM virtual machine that we will be using. Then in the second session, you will actually get to write code for the virtual machine and add in a few pieces so that you'll be able to run useful code. Then we will go back to the theory and start talking about code generation and how you can implement a very, very simple JIT compiler. Then we will actually get to implement part of the JIT compiler, and we're going to iterate eventually on this style so that over time we'll build up a fairly sophisticated virtual machine and hopefully you will be able to understand how every component of it works. So starting right away with the bulk of what this presentation is going to be about, what are virtual machines? So the most basic definition I can come up with for a virtual machine is it's just a program that executes other programs. Normally, when we're running programs, we're thinking about a physical computer that is executing code. What we're going to be thinking about here with virtual machines is special programs that are designed to execute other programs and how we can make all of that work. So the reason you would normally want to have a virtual machine executing programs instead of executing programs directly on a computer is having a virtual machine allows you to delegate managing resources or managing execution. So a virtual machine can do things like managing memory, managing file handles, managing locks and mutexes, which are things that otherwise the program would have to do by itself. Whereas with a virtual machine, some of that effort can be delegated, and it simplifies writing applications. So that's when things like garbage collectors come in that we may get to at some point in the tutorial. For this reason, virtual machines are also often called managed runtime. People will also shorten that to just say runtime, which is a bit of an ambiguous and confusing term, but just know that generally if I say runtime or managed runtime or virtual machine, those all mean roughly the same thing. So in this tutorial, we're going to be focusing on stack-based virtual machines, and this is just something I want to make you aware of. There are different kinds of virtual machines that exist. The most common kind is a stack-based virtual machine, and that just means that when the virtual machine is executing code, it's taking the arguments from the stack, from a stack, I should say, doing a computation, and pushing the result back on the stack. There's other kinds of VMs that you will see out there. For example, Lua is a register-based machine, so instead of a stack, it uses virtual registers. But we won't cover these in the tutorial. Hopefully, once we're through this tutorial, you will be able to understand how these other kinds of VMs work. But we really just want to focus for now on stack-based virtual machines because it is the most common kind. And OpenJ9, as it turns out, is stack-based. So typically, virtual machines, they don't execute just source code. They execute what are called bytecodes. And a bytecode is really just an instruction for a virtual machine. So the same way that physical computers have assembly instructions, virtual machines have bytecode instructions. But because they're specific to the virtual machine, they can actually be processor independent. So you can have one bytecode language that is specific to your virtual machine, but that same bytecode you can use on any platform. So it's not tied to the specific CPU architecture, which is useful because it fulfills this promise that people have been going after for a long time of being able to compile your code once and running it anywhere. When it's applications written in C and C++, usually you can compile your code for one kind of machine, but then you can't take that compiled code and move it to another machine. You have to recompile it. This is not true with bytecodes. So bytecodes provide portability to applications. Bytecodes are also often designed to be efficiently decoded and interpreted by another program, right? So as I said, virtual machines execute other programs. And the same way that a CPU doesn't execute assembly directly, it executes a binary representation of assembly language or machine language. Virtual machines also will typically execute a binary representation of bytecode. So these are not necessarily human readable the same way that machine code is not always human readable, but you can represent it textually a lot of the time, the same way that that assembly language is a textual representation of instructions. So this is an example set of bytecodes for a virtual machine called base9. It's a fair bit more complicated than the virtual machine we will be using, so I won't go through all of the bytecodes in detail, but this just gives you a taste of what bytecodes can look like. So in base9, all bytecodes are 32 bits. The first 8 bits are an opcode that identifies what the instruction is, similar to CPU opcodes. And then the remaining 24 bits are just an immediate value. All opcodes have the same format. So for example, for an int push constant, which will take an integer constant and push it onto the stack, you will have your opcode, which in this case happens to be 0xf, and then the constant you're going to push is just stored in the immediate part of the bytecode. For instructions like int add and int sub, the immediate part is just not used. So you're using up all the 32 bits for the instruction, but you're only actually using the first 8 bits to represent the opcode. And again, add and subtract, all they do is pop 2 values from the stack, add them or subtract them, and then push the result. The immediates can also be used for other things, not just constant values. So for example, if you have an instruction like push from var or pop into var, which are for moving values from variables onto the stack and back. In this case, for example, push from var will take the value from some variable at an index and push it onto the stack. Now, the variable isn't identified by name, it's just an index into some table. So you can kind of pretend like all your variables just have a unique number, and the number in the immediate represents the variable you want to access. If you want to learn more about base9's instruction set, you can follow that link and it will take you there. Yeah? Base9 is related to OpenJ9 in that it uses OMR. Base9 uses OMR and OpenJ9 uses OMR as well. That's the only relation they really have. Yep. Okay, now normally when we write code, we don't write assembly code directly, right? That's very rare. We do it sometimes, but in general, we don't write assembly code directly. Similarly, we don't generally write bytecode directly. Instead, what we write is source code in some source language like Java or Python or Lua, and then that gets translated to bytecode before we execute the program. So there's a few different approaches to this. A really common one is where you take the source code and you ahead of time compile it to bytecodes, or AUT compile it. This is also sometimes called static compilation, and it's similar to how when you're writing C++ or C, you take C code or C++ code and compile it to machine code before you execute it. But in the world of virtual machines, what you're doing instead is you're taking, for example, Java source code, running it through the Java C compiler, producing Java bytecode inside what's called a Java class file, and it's the class file that then actually gets executed by the virtual machine. So there's this two-step process before you get to the real execution of your program. There are other ways this translation can happen. There are some languages that will do translation to bytecode as the source code is being loaded, so you can give source code directly to the virtual machine, and it will translate it basically on the fly to bytecode and then execute the bytecode. JavaScript is a common example of a language that does this. There's also some languages that will let you do both, like Python and Lua, where you can either have your source code fed directly to the virtual machine, or you can specifically compile it to bytecode first and then give the bytecode to the virtual machine. And there's pros and cons to both, so a lot of modern languages are actually switching to a model like this where you can support both modes of translation. All right, so what is an interpreter? So far I've kind of talked about virtual machines, and I've said that they can actually do a lot of things, right? Because they're not just executing code, they're managing the execution of a program. The part of a virtual machine that is responsible for actually executing instructions or opcodes or bytecodes is the interpreter. It's kind of like the CPU of a program, the CPU of a machine. It's really the part that is like doing execution. Everything else is just helping the CPU provide resources like memory or files or network I/O, etc. An interpreter is really actually quite simple conceptually. It's just a loop around a giant switch statement. And the basic algorithm for an interpreter is just for each bytecode in a sequence, execute some C++ code that implements the functionality of that bytecode. Now here I say C++ code, but it doesn't necessarily have to be C++. It's whatever the language you're using to write your interpreter. But in this tutorial we're using C++, so I'm going to keep things consistent for you here. An interpreter will usually have some sort of instruction pointer, which is similar to an instruction pointer in a CPU, or what's sometimes called a program counter. And all it does is keep track of which instruction we're executing, or which bytecode we're executing. Very commonly, the instruction pointer will not point to the current instruction, it will point to the next instruction you're going to execute, not necessarily the current one. And that's a subtlety that has to be, that you have to keep track of. And usually when you start execution, you point your instruction pointer to the first bytecode to execute. And when it reaches the end of the sequence, that's when the loop terminates and when the program is done executing. And in addition, if you're in a stack-based virtual machine, you will have usually a stack pointer that keeps track of where the top of the stack is, as you would in any common stack implementation. So now I'm going to go through an example that I think many of you will have already seen, but maybe went through it rather quickly. This time I'm going to go through it a bit slower. So we're going to start with just a simple function that just returns 5 plus 6 as integer constant, and it does constant arithmetic. It's very simple. The bytecodes, I'm showing you them on the side, are very straightforward. And we have our instruction pointer that we initialize right away to the very first bytecode we're going to execute. And we have our stack pointer that is pointing to the first available slot on the stack. Okay. Any questions? No? Good. All right. So when we start execution, the very first thing we're going to do is actually bump the instruction pointer, because remember, it always points to the next instruction we're going to execute. So we bump the instruction pointer, and now we execute the first instruction, which is going to push the value 5 onto our stack, which is going to cause us to bump our stack pointer to the next available slot on the stack. Now that we're done executing the first instruction, we're going to bump the instruction pointer again and execute the next instruction, which is going to push 6 onto the stack. Again, we push the stack pointer up by 1. Bump the instruction pointer again, and now we're going to execute the add. What happens when we execute the add is we pop the 6 and the 5 we had previously, added them together, and then push the result 11 onto the stack. Right, that's how we get that value on the stack. We then bump the instruction pointer, execute the return, and then it's whatever else happens when the function returns. That value can go into a variable, it can go to memory, maybe the program terminates at this point and it gets printed to the screen. That doesn't really matter yet. Yes. Conceptually, that gets done atomically. In practice, it's up to you to decide whether you want to peek the two values on the stack first and then pop them off and push the result, or if you want to pop the result first, do the calculation, and then push the result. It's up to you how you implement that, but conceptually, all of that happens atomically. Does that make sense? By atomically, I mean it happens instantly. Right? There's no kind of intermediate state that you could get yourself into where, you've popped things off of the stack, but you haven't yet pushed the result. Conceptually, that never happens. In practice, because all programs have bugs in them, that can happen, but we're going to ignore that for now. Yeah. You're in full control of what's happening on the stack when you're executing an instruction. Okay, now that we've gone over what a very simple virtual machine or interpreter looks like from a high level, I'm going to start talking about TVM, which is the virtual machine we created for this tutorial. So TVM is really intended to be an educational virtual machine. You're not going to use it to run any sort of useful programs. It's very much designed to be easy to understand, but at the same time, it doesn't hide any details. So a lot of times, if you look at so-called real virtual machines, they have a lot of complexity in them that may be difficult to understand when you're first starting out, which means that you kind of have to ignore parts of it. TVM tries to expose as much as it can to you in a simple way. So it intentionally doesn't use OMR so that you really get to learn how the internals work. That said, so the name TVM, by the way, stands for Tutorial Virtual Machine. That's just because we're not super creative with names. Coincidentally, T is also sounds like tea, which is a caffeinated drink that is lighter than Java, which is coffee. So that's kind of a fun little side note. And also, T is the first letter of Testarossa, which is the name of the JIT compiler I work on. So that's where the name comes from, mostly. The source code for TVM, it actually originated from base 9. So you remember back towards the beginning, I was showing a few examples from base 9. Base 9 is also an educational VM that we created for teaching how to use OMR. So what we did with this tutorial is we took the same basic idea as base 9, took the code, but we stripped out all of the complexity of it except for the very essential pieces you need to execute code. And we also removed all of the OMR parts. So all that's left now is a very, very minimal virtual machine that hopefully you will be able to understand easily enough. Now, as I said, the language is very minimal. So the initial version of the language you will be working with is basically just a calculator. It's similar to a reverse Polish notation calculator if you've ever had to use one of those. If that doesn't mean anything, don't worry about it. Maybe you can look it up on Wikipedia on your own if you're interested. The important thing is to note that it only supports 32-bit integers, and you only do arithmetic with them initially. The base implementation is also not complete, so if you go to the TVM repo right now, what you will get can't execute all of the code that's supported by the language, and that is intentional. Because the goal of the tutorial is for you to complete the implementation of TVM so that it will be able to execute somewhat useful code. Initially, you will start by just completing the interpreter, because that's kind of the base you need to get started. In a later session, you will be also completing the JIT compiler for it. And it's a very, very simple JIT compiler, but it shows you kind of from start to finish what the JIT compiler is really doing internally. And eventually, you will also add more bytecodes so that it's not just a simple calculator. It will be able to do things like control flow and comparisons as well. So this is the bytecode you will start off with. Like I said, it's very, very minimal. The first bytecode that we have is a special end opcode that just designates where the end of a bytecode sequence is. And this is needed for reasons that might become clearer once you actually start looking at the code. We then have the 4 arithmetic opcodes for addition, subtraction, multiplication, division. And then we have an opcode for pushing an integer constant onto the stack. So initially, only end, integer add, integer multiplication, and integer push constant are implemented. One of your first tasks will be to implement subtraction and division. And initially, that will be all that the virtual machine does. And we have some sample programs you'll be able to use to execute this. But it's only how you get started. And eventually, we will add more things to the virtual machine to make it do more interesting things. So if you were to start writing TVM from scratch, you didn't start off with the code we gave you. If you just started completely from a fresh page, how would you go about doing that? Well, the first thing you would probably want is an instruction class, just a class that represents an instruction or bytecode that you're going to execute. Inside it, you will want to know the opcode of that instruction, right, which designates which thing you're actually executing, and then the immediate value. And those are really the only pieces you care about for an instruction. The next thing you will need is your interpreter loop, which again, an interpreter is just a loop around a giant switch statement. You will have a stack that you're going to use to perform your operation, your instruction pointer, and you're just going to keep looping as long as you haven't reached the end opcode. And so you're just going to continue on going until you reach that final end opcode. For each opcode you iterate over, for each instruction you iterate over, you're going to switch on the opcode, and you're going to have one case for each opcode supported by the VM. So for example, in this case, the very first case I have is for integer add. And then what I'm doing here is I'm just calling a function. I don't want to complicate things at this point, so just call a function that is going to do the addition, and we'll worry about how to do that later. And then to push a constant, again, I just call a function that is going to worry about how to actually do that later on. And I get the immediate from that instruction right away and pass it as an argument to the do and push constant function. If you had more bytecodes, obviously you're going to have one case for each opcode, but I think hopefully this gets the idea across of how the shape of the code looks like. Then, when you go to actually implement those helpers, again, it's actually relatively simple. Your do add, it pops a value from the stack, pops a second value from the stack, adds them, and pushes the result. Your integer push instruction, it takes that immediate value that comes in as an argument and just pushes it onto the stack. And that's really all you need to implement an interpreter. This is not a very easy to use interpreter though. It's kind of a bit annoying to work with. So in addition to these basic things, TVM will also provide additional utilities for you to use. So for example, there will be all the data structures already implemented for you for things like representing opcodes, immediate, representing the stack, etc. That is done for you. The definition of the different bytecodes is also provided for you. And an incomplete interpreter loop is already there so that you don't have to worry too much about where to put that. There are also a few helper functions you have for writing some of the code. You will find that when you write an interpreter, a lot of the code is very repetitive. So we give you already some of the functions you would want to use when implementing an interpreter. And TVM also gives you a bytecode serializer and deserializer. And all this is it's kind of like an assembler in that it lets you write bytecode in a text file and then just load it into the VM for execution so that you don't have to be writing the bytecode manually yourself. This also avoids you having to worry about compiling some high-level language to bytecode because that introduces a host of other problems we don't really want to think about at this early stage. And with that, I do want to take a moment to give credit to the people that made this TVM happen. I think you'll be familiar with most of the names on this slide. This is the same group of people that did your initial onboarding. And this is, as it turns out, also the group of people that created TVM. So thank you, Nazim, Annabelle, Jonas, Shaoli, Drew, and me, apparently. Okay, now when I said this presentation is going to be theoretical, I lied. There's just a little bit of setup that has to happen, and I'm just going to show you what it is. You can do it on your own time whenever you want to. There's really not a lot. It's better if you get this done now, ahead of time, instead of when you're doing the tutorial. So the dependencies you will need are just Git, a C++ compiler toolchain that's up to date. I think on Ubuntu it's Build Essential. I need to confirm that's the name of the package, but that should just give you everything you need. And then CMake 3.2 at least. That's all you really need. Once you have that, you can start going through the initial kind of preparation. Did anyone want to install this now? Okay, I see people typing furiously on their keyboard. Am I good? Can I move on? Okay, I'm going to assume I can move on. Yeah, I think these slides will be made available, so it's okay. You can copy and paste them later on if you didn't catch them this time. What version of C++ do you need? 14. Yes, you need a fairly up-to-date tool chain. I believe GCC 6 and up will work, or Clang 4.0 and up will work as well. Still working on it. Yes.
It doesn't matter here to do it on one of the servers.
No, go ahead. You can do it on one of the servers. If you can get the servers set up so that they work with the tool chains and the code we have, that's great. When I did this, I did it in a virtual machine on VirtualBox, just because that was easier for me. But there's really not a lot to set up. If you have a fairly modern system, you should be able to get it working. I think everyone with a Mac should be able to get this working fairly quickly. And if not, ask questions. So once you have your dependencies set up, you can just clone the repository. The URL is there on the screen. Once you have the repository, you can cd into the directory. And then you can create a build directory. And then you can use CMake to configure the build. And then you can actually build. And then you can run the code. That's it. That's all you really have to do. And this is just to prove that you did it properly.
Should we cd to do before running CMake?
Yes, you should. There's always something I miss in these slides.
Does anyone know what CMake is?
Does anyone know what CMake is? Does anyone want to know what CMake is?
Yeah.
Yes? Okay. Well, so CMake, have you ever used Make? Okay, kind of, maybe? All right. So when you have a project that is several hundreds of files and several millions of lines of code, typing the GCC command manually every time you want to build gets annoying really quickly. So what people have done is they've created build systems that take care of configuring your build. So CMake is actually a tool that will emit make files for you, so that then you have your CMake configuration, and it figures out how to actually build, what the compiler needs to use is, what the compiler flags have to be, how to enable optimization. All of that is taken care of for you by CMake. And that's all it is, really. Okay, so yeah, you could also like write your own make file. That gets to be very, very tedious. And have hundreds of files, and each file needs like special things because your code is weird and it has to be compiled in very special ways. CMake just takes care of that for you, and it makes building things way easier.
It doesn't work on the 7.
Yeah, I expected that. Yeah, that's because I think by default the version of the compilers on RHEL 7 is too old. Yeah, that's too old. I think you need at least GCC 6 for this to work. Anyone still needs the slide? People figured out that you need to CD into build before you run CMake. Okay, so I'm going to move on. And if people want me to go back to the slide, they can ask me afterwards. So you do kind of have a little bit of homework for this first session. It's not a lot. What you should be trying to do first is just reading through the code to become familiar with it. There's not a lot of code, again. TVM is designed to be very small and very simple. So hopefully it will be fairly easy for you to just read through parts of the code and generally figure out what the code is doing. To get you started, these are the 3 directories on the side that are important in TVM. TVM itself is the TVM directory contains the core implementation of the virtual machine. That's where the interpreter and the bytecode serializer and all of that is. TVM run, I think it just contains one file, main.cpp, probably also a CMake file to build it. And all that is it's just a little bit of code so you can generate that executable from the previous slide, that run tvm-run. That's all that's in that directory. And then there's a test directory that just contains some sample bytecode files. So just very, very, very simple programs you can use to test things and make sure that the virtual machine is working. Okay, now for the last part of the presentation. Yes, this has been a bit long, but it's okay. This is the very end of it. I'm going to give you some tips for reading code. Since I give you the task of reading the code for TVM, I'm going to try to help you out and give you some tips generally for reading source code. So why I'm doing this? Well, good programmers read code. You've been working here long enough now that I think you will have realized most developers don't spend most of their time writing code. You spend most of your time reading code. So being able to read code effectively is important, and it might be surprising, but it does take practice to get good at reading code. What do I mean by reading code? I mean not just being able to read what the language is saying, but it's really understanding what the code is trying to do, right? Programming languages provide abstraction mechanisms, and when you write programs, you use those abstractions to express what your program is intended to do. So when you're reading the code, you have to be able to understand what the programmer intended the code to mean. And that, it can be tricky sometimes, especially when you're starting to read more advanced code. And when you're navigating large code bases like OpenJ9 and OMR that are over 1 million lines of code, you have to really get a strategy for being able to find the parts of the code base you're actually interested in and being able to look for the pieces that you might be missing without having to read the entire thing, because that will take a very long time. So, reading code effectively is, I think, a key to becoming a good developer or a better developer overall, which is why I am spending the time here explaining this. Okay, any questions about that? No? Okay, good. So with tip number 1, it's divide and conquer. Okay, you don't need to understand everything right away when you're reading code. Well, again, if you're reading a code base that is millions of lines of code, it will take a very long time for you to read everything. So you generally you don't need to understand everything right away. It's okay to just start learning or understanding one section at a time. One thing you often want to do is just start by looking at the structure of the code and identify sections that are small enough for you to be able to digest. And just read that part of the code, try to understand what it does. And once you think you understand what it does, you can mentally put a black box around it and then just kind of treat that section of code as the part of the code that does this. And you mentally just leave it at that, and that will help you not get overwhelmed with the amount of information you will be seeing when you're reading through the code. So tip number 2 is don't get lost in the details. So programming languages often require a lot of syntax to explain simple things. Don't get lost in those details. Really try to focus on what the code is intending the code is intending the program to do. You don't need to understand like all of the details or what every single function does. You just really need to understand what it does at a high level, and you can let somebody else worry about the details. A lot of times, you don't need to follow every single function that gets called. Right? If you try to do that, again, in a code base that has 1 million lines of code, that will take you forever to read through every single function. And a lot of times, not always, but a lot of times, you can figure out what a function probably does without looking at its code and just look at what its name is, what are the name of the parameters, what is the return type, what are the types of the arguments, etc. The typical example for this is std sort. You don't need to know how std sort is implemented. You don't need to know if it uses quicksort or merge sort or bubble sort or whatever algorithm you might want. You just need to know that it sorts, and that's it. So when you're reading code, try to kind of keep this in mind, that you're just trying to figure out at a high level what things do. Tip number 3, use a rubber duck. So over here, I have a tiny rubber duck. I really like this one because it's small and it can fit in your pocket. So if you're ever in an emergency and need to read code really quickly, you can just pull the rubber duck out of your pocket and it will help you. This is a very common technique for debugging code. That basically the way it works is you take your rubber duck and you explain to it what your code does one line at a time. Has anyone heard of rubber duck debugging? 1, 2, 3, 4, 5. Okay, a few. If not, you can go ahead and read the Wikipedia article about it. I find that teddy bears, stuffed animals, and other inanimate objects also work really well. You'd be surprised the things I've seen used as rubber ducks. Sometimes you can also try using a real person, like getting your buddy and treating them as a rubber duck. The problem with using people is people have opinions, and the opinions can sometimes get in the way. And a rubber duck, I can tell you right now, does not have opinions. So it can actually make things easier. I highly recommend this approach for reading code, by the way. Tip number 4 is experiment, right? If you have the code, and if you can build it, try building it. Try running the code if you can. Sometimes you can't because the thing you're debugging happens to be that it fails to compile. But still, you can still try. If something isn't working the way you expect it to, try changing the code to see what happens. A lot of times, it's actually useful to try to break the code to get it to fail somehow or to crash, because that can tell you that, okay, at least I understand that if I do this thing wrong, it breaks the way I expect it to. And if you kind of go through the code one step at a time, you can find that you can actually learn quite a bit about how the code works by going through an exercise like this. You can also try running the code in a debugger. If you're good at using a debugger, you can try stepping through the code and seeing how variables are changing as you step through the code and what is happening to the environment as you run the code. Finally, tip number 5, and the last tip on this set of slides, is use the resources you have. So search engines are your friend. Most people use Google. I think most people would have put Google, but I always get ticked off when people put Google because I don't use Google. I use DuckDuckGo. I have a thing with ducks, apparently. Just use a search engine, whichever one you like, and search for things if you don't know what they are. If there's syntax you're not familiar with, try searching for that online. You look for answers on Stack Overflow. There are tons of stuff you can find on Stack Overflow. I'm sure most people here are familiar with Stack Overflow. Even if you can't find specifically answers about like TVM, because we literally just created it, so it's unlikely someone is already asking questions about it on Stack Overflow. If they are, I'm impressed with ourselves. You can find information about general virtual machines. Like I said at the very beginning, a lot of virtual machines share the same basic structure. So if you understand how one virtual machine works, it's fairly easy to understand how other ones work as well. And you can find lots of information online about how Lua works, how Python works, how Ruby works, etc. And finally, if all else fails, try asking for help. Hopefully you know people that are willing to help you and that you haven't annoyed them too much, that they won't be willing to provide help. Try asking them on Slack. Again, on Stack Overflow, you can try asking for questions. If you're working on a specific project, you can open issues on GitHub to ask a question. And if you happen to know the person personally, you can also try asking them in person. Yes?
I'd like to add to this. When you do stuff online, it's very easy to go down huge rabbit holes and then just lose all sight of what it is that you were actually doing.
Yes.
And that's completely normal. A lot of the concepts that you're dealing with there, broad topics, education, not very stuff.
Yes, this is very true. Yes, but for the recording, Drew is saying that, yes, when you're searching for things, it's very easy to follow what I think is called the Wikipedia game, where you keep finding things that you don't know what they are, and so you keep searching them, and eventually you have like 20 tabs open with things that you're trying to figure out what the heck it is, and you get completely lost because it's too much information. So when you're searching for stuff online, or through a search engine or Google, whatever, the first tip I gave about, or I guess that was technically the second tip, don't get lost in the details. Don't try to understand everything right away. That tip still holds. Focus on the pieces that you can understand and go one piece at a time and kind of mentally simplify things for yourself by putting them in mental black boxes. So are there any questions about reading code? No, excellent. So why do I tell people to read code and why do I put so much emphasis on it? Because I did say that I think it's an important way of becoming a better developer. Well, in my opinion, the golden rule of programming is write code the way you want other people to write code that you will have to read. So when you see code that is really hard to understand and you're going, what the heck is going on? I can't figure anything out. Use that as a lesson to you not to write code that way. Write code the way it was when it was easy to read, easy to understand, and you could figure out easily what it was doing. That's the kind of code you want to be writing. And with that, thank you for your time. Are there any questions? No questions. Everything was perfectly clear. Oh, either that or everything was confusing. Yes.
So, can you summarize the difference between baseline and how are they different? Why are they different?
How are they different? What is the difference between TVM and Base9? Base9 is a virtual machine that is intended for learning how to use OMR. It has a fairly complex set of features to take advantage of the functionality in OMR. TVM is a very minimal, simple VM that happens to share some code with Base9, but it's completely different in that it's specifically targeted at learning how the internals work. So hopefully by the time you've gone through the tutorial, you'll be able to understand at a high level what OpenJ9 is doing under the hood, or what OMR is doing under the hood, or what any virtual machine is doing under the hood, really. You will also probably understand why a framework like OMR exists to make writing virtual machines easier, because there are parts that get very repetitive and that are fairly complex. So that's really, I would say, the big difference between TVM and Base9. TVM is very much intended to expose all of the internal details of how the virtual machine works while also keeping them simple. Base9 depends on OMR, TVM does not. Yes.
And then in terms of the front end,
oh, right. I guess Base9 has a front end. So Base9 is actually a virtual machine for a JavaScript-like language. And we have this ahead-of-time compiler that will compile this JavaScript-like language to bytecode. Yeah, that's called the front end, depending on which textbook you're following. Some textbooks use different terminology. But anyway, that's what's called the front end. TVM, again, does not have a front end because we don't want to deal with the complexity of having that translation from a high-level language to a low-level language. We want you to be able to just write the bytecode directly that you want to execute and have exactly that be the input to your virtual machine without going through intermediate steps. Other questions? Yes, that's why there's a serialize and deserializer for the bytecodes. It's so that you can write bytecodes as text. Other questions? Yes? The relationship between, I think that question was asked at the beginning, or something very similar. Yeah, no worries. So the relationship is not much. Other than they both have a 9 in the name, that's one of the relationships. And the other one is they both use Eclipse OMR. That's really the only things that are related about them. Yes?
So OpenJ9 is an open source Java compiler using
Java VM.
Java virtual machine, that's right. And this team focuses on the compiler portion of the virtual machine. And all that code is dependent on this other open source project called OMR. So we want people to adopt OMR when they write other language runtimes using OMR, like OpenJ9 is using OMR. But people find it very difficult to use OMR, and they would like to see a simpler version of OpenJ9 to see how OMR can be leveraged to write their own language runtime. So that's why we came up with Base9. And then I guess there's some reason to why we named it Base9. Initially, there were only 9 opcodes, but now it's way more than 9 opcodes. Basically, Base9 also uses OMR. So it has a third-party directory, like basically depends on this third-party project, which is OMR. And then it tries to use some of the key features within OMR, like the compiler, basically demonstrate to people that see how easy it is to incorporate OMR into your language runtime, and then be able to enable some of the more advanced optimization features. But I guess for the purpose of this tutorial, we found that baseline sometimes can be confusing because it abstracts too much. People wonder, I'm calling this OMR function or whatever, but how does it really work underneath? People get bogged down by all the abstraction of OMR and how it actually works. So I think that's how TVM was conceived. That it starts from bytecode and through machine instructions. You get to see start to finish.
I'm just curious about the like more information about it. So was it created for a specific target audience or mainly for anyone who wants to learn how to use OMR?
It was a general.
Oh, okay.
Yeah, so something that we need to be mindful about TVM doesn't involve too complicated. Baseline at one point was very easy to understand, and it evolved into a much bigger, more complicated with one TVM. Phase evolved.
Any other questions? Okay, go do your homework.